Hi folks, I'm Professor Rad and I'm here with my cat Lenny. I don't know if you'll be able to hear him purring or not, but he's here for some emotional support for this video, I guess. This is because the standard normal curve problems tend to be a little bit tricky, so I wanted to do a few more examples before we dug into the central limit theorem and hypothesis tests. So let's do a couple examples together of some forwards problems with the standard normal curve. So for our first example, it says the lifetimes of refrigerators are normally distributed with a mean of 14 years and a standard deviation of 2.5 years. Now, before I even go to read through parts A and B, I'm going to pause and summarize the information I've been given. When I summarize the information, I want to make sure I'm summarizing it with the appropriate symbol and with the number and with the label. So all of those things are going to be important. So first, I noticed that they're telling us that these refrigerators have a mean of 14 years. So because this is for all refrigerators, that means this is population information. So I'm going to use mu to represent the mean, and I'm going to say that's equal to 14 years. The other piece of information from this first sentence that's going to be important is that we have a standard deviation of 2.5 years. Again, this is about a population, so I'm going to use the population symbol for standard deviation, which is going to be sigma. So sigma is equal to 2.5 years. Okay, so now that we have kind of that global information summarized, we can proceed to read through part A. So in part A, what is the probability that a refrigerator will last more than a decade? So when I'm summarizing this question, the first thing I'm going to look for is an X value. So the X value is going to vary depending on what it is you're talking about. Like on this problem, we're talking about lifetimes of refrigerators. So we want to look for something about a lifetime of a refrigerator. So in this case, we're looking about refrigerators that last more than a decade. So the lifetime we're interested in is a decade or 10 years. So for part A, X is going to be 10 years. All right, so now we've collected all of the information that we need to know for part A. And I did want to point out, I don't want to skip over this, but in that first sentence, it also is telling us that these are normally distributed. So that's providing the context that allows us to do this technique. All right, so after you collect all of your information, the first thing you're going to want to find for a forwards problem is the z-score. So our formula for z-score is x minus the mean over the standard deviation. Now I've also put parentheses in the numerator because I have a tendency to forget to type them into my calculator. So I want to make sure I do that so I have them there. Now, because we took the time to summarize all the information that was given to us with the variable and the number, it's nice and easy to plug into this formula now. So I know that x is going to be 10, mu is 14, and sigma is 2.5. So one of the things that can make this problem more difficult is if you do not do that summary, you're more likely to put numbers into the wrong places in the formula. So you want to make sure you take the time to do that summary at first, and that will make evaluating the formula a lot easier. And then this is just a plug and chug. So throw this into a calculator, and it gave me a negative 1.6. So when I'm writing a z-score, I always want to write my z-score to the nearest hundredth. Sometimes that means rounding, or sometimes, like in this case, it means tossing in an extra 0. The reason I want to make sure my z-score is always given to the nearest hundredth is because when we use our standard normal table, we need the hundredths place to help us figure out the area to the left. So, all right, so yes, now we've got our z-score. Next, we're going to want to draw a picture. So I'm going to draw a standard normal curve, and I'm going to plot that z-score of negative 1.60 on there. What makes this a standard normal curve is that you can see I put 0 in the middle for the mean. And I'm not going to be super picky where you put that negative 1.60, other than it should be to the left of 0. So as long as the negative number is to the left of 0 and positive numbers are to the right of 0, you'll be fine. Next, we need to figure out how are we going to shade this curve. So to determine how to shade this curve, I do have to go back to my question. And I want to look for some directional information, either more, less, or between. So in this case, we have the probability that our fridge is going to last more than a decade. So because we're interested in it lasting more, that means I'm going to be shading to the right. If it had been less than, I would have shaded to the left. The last thing we're going to do to complete our picture is to draw an arrow underneath the z-score pointing to the left. The arrow always points to the left no matter what we're looking for. So the shading tells us what we're looking for. The arrow goes to the left. The reason the arrow is always going to go to the left is because the standard normal table only tells us areas to the left. So speaking of, that's where we're heading next. So we want to look up our z-score on the standard normal table. Now this is the side that has the negative z-scores. So to find the area, I'm going to use that left column where it's called z to look up the first 2 digits. So that will tell me the row. And then the column comes from the hundredths place. So because our z-score was negative 1.60, I'm going to be in the row that has the negative 1.6, and I'm going to be in the column that has a 0. If it had been like negative 1.64, then I would have had the same row, but the column would have been over where it says 0.04. So whatever the last digit is, that's going to tell you what to look for the column. So in this case, that row and column intersect at the number 0.0548. So that's telling me the area. So I'm going to throw that here, 0.0548, and I put that on the arrow. Now, again, why we have this arrow pointing to the left is because this tells us what area we have. We have this orange area right now. So we know that this orange space is 0.0548. That's fine, but we want to know the area above. So we want to know the purple region. So because this is a greater than question, because we need to know the area above, we're going to subtract 0.0548 from 1. Remember that the total area underneath a probability density curve is always 1. So basically what we're doing here is we're finding a complement. So if you have a more than question or a greater than question, you subtract the table value from 1. And in this case, we're going to get 0.9452. Okay, so we're almost done now. After you find your answer, you want to make sure that your answer is in the correct format. So going back up to this question one last time, it says, what is the probability that a refrigerator will last more than a decade? So our key word here is the probability. So if it says probability or proportion, that means we want the answer in decimal format. So because we want probability, we want our decimal answer. If it says percent, then we're going to change that into a percentage. But for probability, keep it in decimal form. Okay, so let's do part B together as well. So let's clear out our slate a little bit. And I'm going to keep that summary information. So I'm keeping that mu is 14 and sigma is 2.5, because that was the sentence above parts A and B. That's the global information that we have. Now let's narrow our attention and look at part B. It says, what percent of refrigerators last between 12 and 15 years? So remember, the first thing we want to do is determine an X value. So because this problem is about lifetimes of fridges, we want to find lifetimes of refrigerators. So here it's asking between 12 and 15 years. So this means we're actually going to have 2 values for X. We're going to have one X value that's 12 years and another X value that's 15 years. So that's okay. You'll either get one X value or 2 X values. Our biggest problem right now is that 2 X values means we have to use our z-score twice. So we'll just work through it one at a time, and let's focus on X being 12 years. We want to find the corresponding z-score. So z is always going to be X minus the mean over the standard deviation. So we're going to use the X of 12, and then we plug in the 14 and the 2.5 accordingly. So basically right now we're just ignoring that 15. Once we find those values, I'm going to write this on the side, we get a z-score of negative 0.80. Now we'll repeat this process for X being 15 years. So I'll do my formula again. And this time I'm going to substitute in 15 for the value of X, still keeping 14 for the mean and 2.5 for the standard deviation. When I simplified that one out, I got z was equal to a positive 0.40. All right, so that's like the first step is finding the z-scores for both of these values. Next, we're going to want to draw a curve. So let's give ourselves some space here. There we go. And I'm going to draw that first z-score first. So negative 0.80, because negative 0.80 is a negative number, I'm going to draw that on the left of the 0. When I draw the second z-score, it's a positive 0.40. So I want to make sure that goes to the right of 0. So I've graphed my two z-scores. Next, we want to figure out where do we shade. So for this problem, it says what percent of refrigerators last between these two values. So because we're interested in a percentage that's between the 2 years, we're going to shade between our two z-scores. Lastly, we're going to draw the two arrows underneath, one from the negative 0.80 and the other from the 0.40. Notice that when I drew the arrow for the 0.40, I made sure to extend it down and underneath that negative 0.80. So this is important because it helps to remind me what the table area really is. So when I look up these values on the standard normal table, the arrow is representing the area that the table is telling me. So I looked these up on the table before. When I looked up negative 0.80, I got a table area of 0.2119. And when I looked up 0.40, oh, sorry, I forgot my animation order. So that 0.2119, that's the orange region on the standard normal curve. Okay, so that's the information we know. We want the purple. Right now, we know this orange amount. When I looked up 0.40, that gave me 0.6554. Now, the reason that 0.6554 is in both orange and purple is because this area from the table is everything to the left of 0.40. In particular, it's the sum of the orange region and the purple region. So 6554 represents these two pieces. We know that the orange piece is 0.2119. So if we want to figure out the purple piece, we can take the sum of them, the 6554, subtract off the orange, the 2119, and that will give us the purple. So that's going to be our next step. When we're finding this purple region, we're going to take the bigger area from the table and subtract the smaller area from the table. And this will always be the case whenever you have a between problem. You're going to look up both areas and then take the bigger area minus the smaller one. In this case, that's going to give me 0.4435. Lastly, before I box that in as my answer, I want to double check the format that they want my answer in. So it says what percent of refrigerators. So because they want a percentage, I have to change my answer into a percent. So 0.4435, I'm going to move that decimal point 2 spots to the right to get 44.35%. And then that's the answer that I'm going to include. Also, by the way, on Blackboard, if it asks you for the answer, this is what that means. It means your final answer for the full problem. And then it'll ask you for other pieces throughout. All right, so that's going to finish up example 1. Let's look at a second example that deals with a different topic. So for example 2, it says, suppose a fast food restaurant finds that the mean time spent by customers in the drive-thru was 142 seconds. Assume the drive-thru times are normally distributed with a standard deviation of 32 seconds. All right, so what I'm going to recommend is that you pause the video here and see if you can summarize the information from those first 2 sentences. So don't worry about parts A and B quite yet. Pause the video and summarize those 2 values, and then you can unpause and check your answers. Okay, did you try it out? So let's see, the first thing I'm noticing here, other than that, we're assuming these are normally distributed. So that tells us we're going to use the normal curve, is that it says we have a mean time was 142 seconds. So because these are the mean times, that means that mu is going to be 142 seconds. The other piece of information they told us here is that the standard deviation is 32 seconds. So we can summarize that by writing sigma is equal to 32 seconds. Okay, so and now that we've got the information summarized, we can go ahead and do parts A and B. I'm going to ask you to pause the video here and try part A on your own. The reason I'm doing that is because part A is pretty similar to example 1B. So the last example we just did, this part A is going to be very, very similar to that. So pause the video, try that out, go all the way through all the steps, and then you can unpause and we'll walk through it together. Okay, did you try out part A? Let's see how you did. So first I want to identify the X value. In the last example, the X values were lifetimes of refrigerators, but for this problem, it's about the time customers wait in the drive-through line. So in this case, we're looking at 100 and 200 seconds. So again, we have two numbers here, so that's going to give us two values for X. We have 100 seconds and 200 seconds. Next, we're going to, now that we've got this information summarized, we're going to find the z-scores. So we're going to use the formula z is x minus the mean over the standard deviation. So for 100 seconds, I substituted that in. This time mu is 142 seconds and sigma is 32 because we summarized that from above. And I got a z-score of negative 1.31. Then I repeated this process for the second x of 200. And I got a z-score of 1.81. So that, again, that's like after you do your summary, that's the first step of solving a forwards problem, is figuring out your z-scores. The second step is going to be drawing a picture. So I'm going to draw my standard normal curve, and I've got my negative 1.31 to the left of 0 because it's negative, the positive 1.81 to the right of 0 because it's positive, and I shaded in between because this is a between problem. It says between in it. Once I've got that all settled, then I'm going to move on to step 3, which is looking up these two areas on the table. So when I looked up negative 1.31, I got 0.2119. And when I looked up 1.81, I got 0.9649. So those are the two areas that I found on the table. Our last step is going to be to subtract the larger area minus the smaller area. So we're going to subtract 0.9649 minus 0.2119. And that gave me 0.753 or 0.7530. So the purple area is going to be this 0.753. And then to figure out whether I want that in decimal or percentage form, I go back to the problem and it says probability. So because it says probability, that means I want the decimal format for my answer. So I'm going to leave it as a decimal. All right, how did you do with part A? Hopefully we did all right. Let's try one more example together. We'll do part B. And we'll start part B together, and then we'll do a similar kind of pause and try it out. So for part B, I'm going to keep the mu and the sigma because that's global information that's true for all of these problems for this example. And now I need to look for the X value. So part B says, what proportion of drive-through times are shorter than 2 minutes? So I'm interested in an X value of 2 minutes. Now there's a little problem with this number here. Can you see what the problem is? Okay, so the problem is that our mu and our sigma are in terms of seconds, but X is in terms of minutes. So be on the lookout for different units. Sometimes that's going to happen. Not often, but occasionally it will occur. So you want to make sure when you include your summary values, you're including those units like we have here of seconds, because you want to make sure everything has the same units together. So I'm going to convert 2 minutes into seconds just by multiplying by 60. So 2 times 60 is 120. So that's going to give us our 120 seconds. Now this problem is going to flow the same way as other forwards problems. So our X value is 120. So that's going to be the number we use in the formula for the z-score. So we're going to substitute that in. And then here's where I'm going to ask you to pause and finish this problem on your own. practice through, see if you can figure it out. And then when you're all done, unpause and see if you get the same thing that I got. All right, did you give it a go? So here we have our 120 minus 142 all over 32. That gave me a z-score of negative 0.69. So next I drew my picture because negative 0.69 is a negative number. I drew that to the left of 0. And because this is a shorter than problem, I'm shading to the left of my cutoff score. The third step is to look up my z-score on the table. So I looked up negative 0.6, that was the row, and then my column was the column that had the 9 in it. And that gave me an area of 0.2451. Now, because this is a shorter than problem, there's actually nothing else we really have to do because that 2451 is the same thing as the region that we are looking for. It's the area below, and that's what we want. So 0.2451 is going to be our answer, unless we have to change it to a percentage. So we do that one last check. In this case, it's asking us what proportion of drive-through times are shorter than 2 minutes. So because they want a proportion, that means they want the decimal answer. So our answer is going to be 0.2451. Cool. So how did we do with this last example? All right, so that's it for these problems. Like I said, I think I said earlier, these problems are going to form the foundation for the central limit theorem and the hypothesis test that we move forward. So this process is going to be very much the same. The only thing that's going to be different for the central limit theorem is we're going to have an extra step at the beginning before we find our z-score. So that's it. And it's going to affect our z-score formula a little bit, but the big picture of x minus the mean over the standard deviation, that's the big picture that's going to be the same for our z-score formulas. So hopefully this helped with those problems a little bit. There are a couple of review problems on this week's check-in. As always, we can go through this in the ILS on Monday if you have questions. So I hope this helped with forward problems a little bit. In the meantime, I hope you have a fantastic day, and I'll see you next time. Bye for now.